So now you can assign oxidation numbers. Let's do the next step and put them into equations where we're considering how many electrons are lost, how many electrons are gained, and thus using those in order to balance the entire redox equation. Start off with a couple of potentially straightforward questions, just thinking about numbers of electrons, starting off with one of your most preferred oxidizing agents, dichromate, Cr2O72-, which in acidic solution ends up going to Cr3+. This is extremely important, not just for this particular topic, but also when you get into oxidations in organic chemistry. Anyway, first thing one must always do is assign oxidation numbers. Oxygen's pretty easy. -2. Even easier is for the Cr3+, their chromium must be +3. This chromium here, we talked about it in the previous movie and several times throughout the whole discussion. 7 oxygens at -2 each means -14. If the whole thing's -2, the 2 chromiums must combine to give you +12, thus each chromium is +6. Now, after assigning oxidation numbers, next most important concept or practice is to make sure you balance the important atoms. We have 2 chromiums on the left, thus there must be 2 chromiums on the right. Now let's think about what actually is going on in this reduction process. Each chromium is going from 6 to 3. So each chromium has a change of 3. We have, however, 2 chromiums, and 2 times 3 is 6. So there's 6 electrons involved in this particular process in the correctly balanced half reaction. Question 9 looks at the surface of it, absolutely horrendous and yuckified, but it's not actually that bad. Okay, we're doing an oxidation, and if you think of the fundamental definition of oxidation, we're adding 2 oxygen atoms and we're losing 2 hydrogen atoms. So it's obviously an oxidation going from toluene to benzoic acid. Now let's study it more closely in terms of the electrons. Start off writing the formulas out properly in a way that we can actually handle them. So yes, there's 6 carbons that you might know by now in an aromatic ring, and 1 carbon that's not in that ring, but for the purposes of this exercise, they're just 7 carbons. Same argument for the hydrogens. Okay, now we know from our oxidation numbers, whatever the carbon oxidation number is in here, plus 8 of the hydrogens is 0. Here, whatever the new carbon is, because presumably it's changed as we got this oxidation going on, plus the 6 hydrogens plus the 2 oxygens is 0. Throw in what is just about always the case when it comes to organic, and that is the hydrogens are +1 each, and the oxygens are -2 each. Okay, now when you look at this, you could now go ahead and say, all right, so the carbon oxidation number in this one is going to be -8/7, and the carbon oxidation in this one is going to be -2/7, but that's not actually necessary, because what we're looking for is how many moles of electrons must be removed from each mole of toluene. So we can think about the 7 carbons as a whole. So let's rearrange that a little bit. Here the 7 carbons oxidation numbers combined must be -8 to balance out their +8, and here the 7 carbons combined must be -2 to balance out what was effectively the +2 that comes from this process. So therefore the 7 carbons between them go from -8 to -2. So the 7 carbons between them have lost 6 electrons per molecule. Okay, we don't have to worry about the fact of what each oxidation number is. All we care about here is the 7 carbons combined to be -8 oxidation number in toluene and -2 oxidation number in benzoic acid. Might need to think about that a little bit, but it does enable you to take a rather sneaky question into a relatively straightforward one. And now let's go ahead and actually balance the equations. Now I've got quite a few of these. I believe there's 11 of these, and it can get really tedious just sitting here going through the same process in detail. So what I'm going to do is I'm just going to detail each particular aspect as we come across it in successive questions, but speed through the rest of them so that at least you see where all the numbers are coming from, even if in each particular one I'm not spending excruciating detail upon discussing each one. So anyway, nitrate and tin, NO3- and SN to make nitrogen 2 oxide, so that's NO, and tin 2 cation. So there's our overall reaction there. Okay, first thing to always do is assign oxidation numbers. Going relatively quickly through here, the tin here must be 0, the tin here must be 2+. Oxygen is always going to be a more important, more significant atom in terms of oxidation numbers than nitrogen because it's more electronegative. So the oxygen is always going to be -2 here. Thus in NO, the nitrogen must be +2. And in nitrate, a little bit more complex, but I'm sure you can do it quite happily in your heads, the nitrogen must be +5. Now let's check and see what's reduced and what is oxidized. Well, reduction is where, not just in red, but the species gains electrons. If it gains electrons, its oxidation number goes down. So therefore the nitrogen goes down from 5 to 2. So the nitrogen is reduced. So we'll pull that out. Oxidation is where the oxidation number goes up because the species loses electrons. So here tin goes from 0 to +2. So it is oxidized. Next step, always balancing important atoms. Here we've got one nitrogen, one tin. So now we can throw in the electron species. Nitrogen, as it's reduced, gains electrons. It goes from 5 to 2, so it gains 3 electrons per nitrogen. There's just one nitrogen, so therefore we say NO3- plus those 3 electrons goes to NO. If it's gaining electrons, we can effectively say it's reacting with electrons, so the electrons are on the left-hand side. Going for the oxidation one tin. Each tin is going to lose electrons because it goes from 0 to +2, and it loses 2 electrons per nitrogen. So if it loses them, it's giving them out. So we put the electrons on the right-hand side. So there is that particular half equation. Tin goes to tin 2+ plus 2 electrons. Now we've got, as far as I'm concerned, the half equations are balanced in terms of important atoms and electrons. So at this stage, I like to put them together and proceed from then on with just one equation to work with. So in order to do that, we have to balance out the numbers of electrons. And so we take 3 electrons here, 2 electrons here. Think of what is the least common multiple of 3 and 2, and it is 6. So how do we turn 3 into 6? We multiply by 2. How do we turn 2 into 6? We multiply by 3. Put all that together, and here is the current state of the equation. Okay, taking the 3 tins on this side, 3 SN2+ on the right-hand side, 2 nitrates on the left-hand side, 2 NOs on the right-hand side, and the 6 electrons that would have been on the left-hand side and the 6 electrons that would have been on the right-hand side cancel out. Moving to the second slide of this particular thing, here we are. Next thing to do is check out the charge. Okay, total charge on the left-hand side just comes from the nitrates. There's 2 of them, so 2 times -1 is -2. Total charge on the right-hand side comes from the tins. 3 times 2+ is +6. So our charge is in deficit by 8, okay, -2 going to +6. Now what should we use to balance that charge? Well, we're in acidic solution, so therefore we will use H+. So we have to add H+ to one of these sides in order to balance it out. Now of course when we add H+, we're going to make it more positive, so therefore we need to add these to the more negative side. So therefore we'll add H+ to the left-hand side, and now our charges are balanced. Next thing to look at are the oxygen atoms. Fairly straightforward. Oxygen only occurs in the nitrate on this side, 6 of them, and the NO on this side, 2 of them. So they are in deficit by 4. So therefore we've got to add in 4 oxygen somehow without messing up the charge, without messing up the tins, without messing up the nitrogens. And of course we're in aqueous solution, so we do that via water. What side do we do it on? We do it on the side that needs more oxygens, which is obviously the right-hand side. So pop in 4 waters on the right-hand side. And now finally we need to check the hydrogens because we can do nothing else. 8 hydrogens on the left-hand side, 4 times 2 are 8 on the right-hand side. So our hydrogens are balanced, nice big smiley face. Hopefully you followed all of that, especially after the ones that we did as examples. Another fun equation was the coefficient of water. Well, only way we can know that is when we balance the whole thing. We look at it, there's our favorite oxidizing agent, dichromate, so we know the chromium's +6 there. Iodide, obviously the iodine is -1, chromium must be +3, iodine must be 0. So what's reduced? The species that goes down in oxidation number, so the chromium is reduced. What's oxidized? The species that goes up in oxidation number, so thus the iodine is the species that is oxidized. Now let's go through each of these half equations and fill them up in turn. Next thing to do, must not forget this, is to balance the important atoms. So we've got 2 chromiums on the left, we must therefore have 2 chromiums on the right. Once we've done that, we look at each chromium, we say it goes from 6 to 3. Thus each chromium is going to gain 3 electrons. The only way you go from +6 to +3 is to gain electrons, gain 3 of them. We have 2 chromiums, so therefore we need 6 electrons on the left-hand side. Okay, remember reduction is always where electrons go, on the left-hand side. Hope I said that right a minute ago. Left-hand side, because you are gaining electrons, you are reacting with electrons. And of course, R for reduction, R for reacting with electrons. Let's go back to our oxidation one. Again, we see that we've got an imbalance in the important atoms. We need 2 iodides to go with the 2 iodine atoms in iodine. Oxidation is where a species loses electrons. Each iodine goes from -1 to 0, so each iodine has 1 electron. There are, however, 2 iodines, so we need 2 electrons, and because it's losing electrons, we say it produces electrons, so the electrons go on the right-hand side. So now we put these together before we continue on. We got 6 electrons, we got 2 electrons, we've got to manipulate these so they balance out. How do we turn 2 into 6? We multiply it by 3. And of course, how do we turn 6 into 6? We multiply it by 1. So putting that together don't affect the chromiums. Still got 1 dichromate, 2 chromiums, but we have to multiply the species in the oxidation half equation by 3. So 2 times 3 is 6 iodides, 3 iodines there. Enough space here, so let's continue on to finish off. Once we've got this part of it, in which we have balanced the important atoms and balanced the electrons, next thing to consider is the charge. Total charge on the left-hand side is -8, so got -2 there, and 6 times -1 is -8. Total charge on the right-hand side is +6, so that's a difference there of 14. We're in acidic solution, so we use 14 H pluses to balance it. What side do we put the H pluses on? The side that needs to become more positive, so that's this -8 needs to become more positive. So we pop those on the left-hand side. Next, examination of the oxygen atoms. 7 on the left-hand side, none on the right-hand side. Obviously, difference in 7. We're in aqueous solution, so we use water in the equation to balance those out and put those waters on the side that needs more oxygen, so obviously the right-hand side, giving us this species. And then finally, we'll check with the hydrogens. We've got 14 hydrogens on the left. We have 7 times 2, or 14 hydrogens on the right. And so we are nicely balanced. And another one, let's write it out nicely for us here. Last question, we had to worry about balancing a number of important atoms. But it was kind of a poor one to start with, other than just to emphasize the concept, because if you forgot to do it, you'd end up with the right answers. This question here, reinforces the balancing important atoms, but also brings in the idea not just of having oxygen in compounds, but hydrogen in compounds as well, and how you have to remember to take that into account in the process. So anyway, it's the sign oxidation numbers. Really nothing to write home about here, nothing exceptional. Iron is of course reduced, and the nitrogen is oxidized. So let's follow the reduction one through. Reduction where something gains electrons, species gains electrons, going from 3 to 2, 1 electron per ion. There's only 1 ion on each side, and so that is the half equation for the reduction. Oxidation, of course, losing electrons, going from -1 to +1. Got to make sure we balance the important atoms. We have 2 nitrogens over here on the right, so we've got to have 2 on the left, so 2 of the NH2OH2 pluses. Each nitrogen is going to lose 2 electrons, going from -1 to +1, but we have 2 nitrogens, so thus we need a total of 4 electrons being produced, 4 electrons coming from the oxidation. And we got to balance the electrons by putting them together. We got 1, we got 4. How do we turn 1 into 4? We just multiply that by 4. And so this is that nice equation in which the electrons and the important atoms are balanced. Now moving, of course, to the charge. Total charge of 14 on the left-hand side. Can be nasty when you've got sort of these big coefficients, but 4 times 3 plus is 12, 2 times 1 plus is 2, 12 plus 2, 14. Over here, the only charge coming from the Fe2 plus 8. So we got a difference of 6. We're in acidic solution, so therefore 6H plus. Which side needs the H plus? Side that needs them the most needs to become bigger in terms of the charge, so thus the H plus goes on the right hand side. This also illustrates another extremely important concept. You put the things where they're needed. There are teachers who say H plus always goes on the left hand side. Well, it does 95% of the time, but when your examiner is a sneaky little person and gives you one of the 5%, well, it comes on the right. So always be aware, you put your H pluses, you put your waters, etc. on the side that needs them. Now let's think about the oxygens. Got a total of 2 oxygens on the left, 1 on the right, so a difference of just 1, which will be balanced by water. Which side will the water go? Well, again, onto the right, because that is the one that needs it. So again, you have teachers who say that the H2O always goes on the opposite side of the H+, and it does 95% of the time. Okay, so finally, let's check with our hydrogens, and this is going back to what I mentioned at the start. You have to keep really good track on the hydrogens in this particular one. So on the left-hand side, we have a total of 2 plus 2 is 4 times 2 is 8. And on the right-hand side, we got 6 plus 2, which is also 8. And I hope that merits a smiley face. By the way, I've been kind of skipping what the actual question is asking for. We're asked for the coefficient of the water here. The coefficient of the water is 1. Question 13 brings in another sneaky little bit of business here. You might notice there's peroxide. So in this case, the oxygen is not just going to be one of those standing atoms that we have to balance it. It's also going to be associated with the redox process. Easy to see that with peroxide, not necessarily as easy to recognize it with water, but that's okay. Don't panic. Let's just go through following our process. So assigning oxidation numbers. I won't dwell on those, but relatively straightforward. What's reduced? The oxygen is reduced because the ions are oxidized. So starting over this side, balance the important atoms. What's the important atom that we have? Well, oxygen. Got 2 on the left, so we need 2 on the right. Now, each oxygen goes from -1 to -2. So each oxygen has 1 electron, has gained 1 electron per atom. We have 2 oxygens, so therefore we need 2 electrons on the left-hand side. Oxidation, very, very straightforward. 1 ion, 1 electron per ion, and so just fairly nice and easy, 1 electron oxidation. Bringing them together, we've got a 2 there, 1 there, so we'll just multiply this by 1, this by 2. And that is our pretty little equation in which the important atoms have been balanced and the electrons have been balanced. Let's do charge. 4 plus on the left, 6 plus on the right. So difference of 2, we need 2 H pluses, going to go on the left-hand side. Now let's do the oxygens. 2 on the left, 2 on the right. And so we don't need any more waters. And that can sometimes freak students out. But I've got to add in some more water. Not if everything's nicely balanced, you don't. So let's check our hydrogens. Got a total of 2 plus 2 or 4. 2 times 2 is 4. And again, hopefully merits a smiley face. So while we got hydrogen peroxide on the brain, let's do the decomposition of hydrogen peroxide. Now this is a decomposition reaction because it is one species that produces 2 or more species. However, if we look at the whole oxidation number process, we see that this is also a reaction that is a disproportionation. The only thing that changes in terms of oxidation number is the oxygen. The oxygens all start at -1. Some of them turn into -2. Some of them turn into 0. Disproportion reaction in which one species acts as both the reducing and the oxidizing agent. One species that contains the atoms that are going to be oxidized and those that are going to be reduced. So the reduction is H2O2 goes to H2O, that's the oxidation number going down. The oxidation is the H2O2 going to O2, that's the oxidation number going up. Balance the important atoms, got 2 there, need 2 here, so we need 2 waters. Each oxygen gains from -1 to -2, so gains 1 electron, and so we got 2 oxygens, so therefore we need to gain 2 electrons. Over on the oxidation side, we got 2 oxygens, so that's great. No need to worry about extra numbers of oxygens there. Each oxygen goes from -1 to 0, so each oxygen loses 1 electron, again 2 oxygens, so 2 electrons involved. Putting these together, no need to mess around with anything in terms of multiplying them because we've got 2 electrons on each side. And so here is that equation in which the important atoms are balanced and the electrons are balanced. Let's check charge, all zeros, no problem there. Let's check our oxygens, 4 there, no issues there. Let's double check with hydrogens, 4 on the left and 4 on the right. Okay, so not actually that tough when it all comes down to it. You could actually balance it by inspection, but it is very definitely worthwhile just pointing out how you do a disproportionation reaction. Another disproportionation reaction, manganese dioxide, starting off here, going to Mn2 plus and MnO4 minus. So one source of the manganese is going to 2 plus and the manganese 7, as we can see when we look at these oxidation numbers. So what is reduced? Well, the MnO2 is reduced, going from 4 to +2, goes to Mn2 plus. And what is oxidized? Well, again, the MnO2 is oxidized, going to MnO4 minus there, the permanganate. 1 manganese in each of these, so we don't have to worry about balancing important atoms. Gaining electrons on the reduction gains 2 electrons. Each manganese goes from 4 to 2, so gains 2. So we need 2 electrons on the left-hand side. Over on the oxidation side, in which the species is losing electrons, we go from 4 to 7. So therefore, each manganese gains 3 reactive electrons as products. So how do we turn 2 and 3 into the same number? We just cross multiply, giving us the equation in which all the manganeses are balanced and all the electrons are balanced. However, unlike the previous disproportionation reaction, we do have charges and extra oxygens and all kinds of stuff. So let's proceed to the next steps. Charge, 0 on the left, plus 6 on the right. From here, and then 2 minus here, so 6 minus 2 is +4. So a difference in 4. Again, we're in acidic solution, so we need H+, which will go on the side that needs it. The one that has the smaller charge, that's the left-hand side. Now check the oxygens, 10 on the left, 8 on the right. Difference of 2, so we need 2 waters. What side should we put those on? We'll put them on the right-hand side, as that's the side that needs more oxygens, giving us that. So now checking the hydrogens, total of 4 on the left and none until we get to the water, 4 on the right. Thus we are nicely balanced. Now we have the reverse of a disproportionation. We got 2 reactants but 1 product. And so this would be called a synthesis reaction without a redox part of it, as it is a redox equation. So you see -1 going to 0 plus 5 going to 0. It's a conproportionation reaction. What's reduced? Well, the Cl in ClO3 minus is 5 going to the Cl in chlorine, which is 0. So that's the reduction. The oxidation, Cl minus and -1 going to Cl2 at 0. So that's the oxidation. Focus on the reductions. 2 chlorines on each side. Each chlorine goes from +5 to 0. So that is 5 electrons per chlorine, 2 chlorines, so 10 electrons overall here. For the oxidations, again, we need 2 chlorines on both sides. So 2 in front of the chloride. Losing electrons, each one loses from -1 to 0, so loses 1 electron. We have 2 chlorines, so we need 2 electrons on the right-hand side. Got 2, we got 10, put them together. I have to multiply the 2 by 5 to get 10, and we get this reaction here. Now at this point you could proceed with this, or you could recognize, well, I can reduce this by dividing all the coefficients by 2. 10, 2 and 6 turn into 5, 1 and 3. Just makes it prettier and nicer, and ultimately when you're all said and done you should always use the lowest possible integers to balance equations. Now we've got minuses and oxygens floating around, so we do need to take a closer look at everything else to balance it. Charge wise, we've got a total of -6, -5 plus -1 is -6 on the left hand side, 0 on the right hand side. Difference of 6, we are in acidic solution, so we need H+, which goes on the side that needs it most, which is the left hand side. Look at the oxygens now, 3 and 0, so therefore we need 3 waters on the right hand side. Now check the hydrogens, 6 on the left, 6 on the right, so we're in good shape. Ask for the Cl- to ClO3-, Cl- 5, ClO3- 1. So there we are, a conproportionation reaction.